right, thank you, Alex. Hey, everyone, thanks for being here. Sam Shehata. I've been here for under 2 years at Langley. It's been a wild ride so far. So these are my collaborators. It's a pleasure working with Ashley Corzon. I inherited the aerodynamic database from her, and she's really been guiding me and helping me through the transition. Bill Klebb from the aerothermal group. He's been providing a lot of the safety work, sketch to solution process, and a lot of other safety supports in the project. And of course, Mark Schoenberger, he's the aero lead for MAV at Langley. He's been a great mentor so far. And Bill Crosby, who is retired, he's the person who ran the 14 by 14 inch trisonic wind tunnel tests for the study. So moving forward, I'm going to break this talk into four main parts. First is going to be the mission architecture of MAV and where it falls within the operation of returning samples from Mars. Then we'll transition into the aerodynamic database and how we do aerodynamic modeling in our branch. It can be done in many different ways, but within our branch, we do it in a certain way. Then we will compare some supersonic static aerodynamic data between the wind tunnel and the CFD study, and followed by the requantification of the uncertainties that we carry from these comparisons and how we incorporate these uncertainties into flight trajectory analysis into post-2 descents or whatever other flight simulation models. And final conclusion. Okay, so mission architecture, MAV, it's not the MAV, it's a MAV, Mars Ascent Vehicle. If you're thinking about launching humans from Mars and stripping down its nose cone and slingshot out of Mars orbit, then puncturing a hole in your spacesuit and using that as a thruster to get to your rescue crew, I hate to tell you that's not the case here. Not everyone's Mark Watney, although the no-nose design might have been inspired by the movie itself. Thanks to JPL, but obviously this is aerodynamically questionable, and here we are with the data to speak the facts. So where does MAV actually fall within the return sample from Mars? And I like to always play this video. If you haven't seen this, it is online. If you have, sit tight, and I'm not going to play the whole video. Okay, to be continued. Yeah, so as you can see, there's a lot of different components, different vehicles. The SRL, the Sample Retrieval Lander, it serves as a launch platform for MAV. Obviously, the Perseverance rover is already there collecting samples, working hard collecting samples near the Jezero crater. And obviously, the MAV is 10 feet tall. Obviously, this is just the very early numbers. We are continuously changing the design. And many centers are working on it. Ames working on it, Marshall Space Flight Center, JPL, and also Lockheed Martin. They're responsible for developing the vehicle design and its integrated system. Just quick numbers. The MAV is going to be about 900 pounds, 370 pounds on Mars. It's about 1.6 feet wide. Again, these are always changing just to make sure it fits into the SRO. There are two stages, as you can see. The first stage is the ignition. It's the first It's a two-stage solid propellant rocket. And the second one is when after fairing and coast. Speed of that is 2.5 miles per hour, and time to orbit is about 10 minutes. Okay, so again, you've already seen the video. You kind of noticed the main components of the trajectory itself. It starts off with the vectoring. It's kind of like a toss-up, kind of like what we do with missiles here at DoD. And it's tossed up a little bit harder at the front than the back, so that it orients upwards. It's tossed up several meters high, and of course it ignites and points upward towards the Martian sky. Then it's followed by maybe 75 seconds of nominal burn until MECO, mid-engine cutoff. And when mid-engine cuts off, there's a bit of a transient response when the thrust profile kind of like dies down, it ramps down, then get complete mid-engine cutoff. And after that, it's coast and fairing separation, then followed by staging, spin stabilized second stage burn, and obviously into Mars's orbit. A couple other videos I want to show. So there's been some tests at JPL already with the toss-up. It's not showing. Okay, the objectives, obviously, you've seen the solid rocket motor stage 1 through the burn. I think this is where we're going to be applying the aerodynamic database construction and development. So really the objective is to develop an aerodynamic database for flight trajectory analysis, mostly done in, we'll post to the NESC group. They do post to here at Langley. Descents has been led by JPL. They run some Monte Carlo runs. In these programs, they integrate the equation of motions to comprehensively define planetary missions and vehicle parameters. Obviously, these models also incorporate other different types of models, like the gravity model, the atmospheric models, mass properties, air thermal, and so aerodynamics is also a crucial part of that. Then moving forward, again, I've already explained that we're getting data from computational tools and wind tunnel experimentation to predict static and aerodynamic forces, and how we're using these data and populating the aerodynamic database. We're also comparing and validating safety results from the 14-inch trisonic wind tunnel and using those results to quantify our uncertainties on a representative vehicle. Again, it's been done a long time ago. The vehicle configuration has already been changing. But when I say representative, it still maintains the same slender shape with a nose and so on. The special focus in the aerodynamic database, especially for this talk, we're going to be focusing more on the continuum flow, supersonic, transonic, and subsonic regimes, so nothing rarefied, although I will speak about how we obtain rarefied flow from our solvers and how we're populating the aerodynamic database from these solvers. So just to start with the aerodynamic coordinate system, it's standard definition. You got all these forces defined and the moments. Axial force, it's acting longitudinally. CN and CY are the normal and side forces. Then you've got the moments generated. You got the pitching moment, rolling moment, and the yaw moment. And the key parameters here is the alpha and the beta. These are normal inputs from the equations of motions from the simulations. There are inputs into the aerodynamic database, and from alpha and beta and Mach number and Newton number, these are general inputs that calls out the static forces and moments at different flow regimes. So moving forward, the flight regimes, that the way the aerodynamic database is partitioned into several flow regimes. High altitudes, low density, free molecular dominates the flow, meaning that the air particles are very sparse, and so continuum assumption does not hold, and we have to revert to specific types of solvers, particularly the direct simulation Monte Carlo, the map code. And with that code, we can obtain free molecular safety solutions and rarefied transitional safety solutions. And you can see here the input parameters for these conditions is Newton number. These are the parameters that we input into the database to call out the static and forces and moments at these flow regimes. Then moving down into hypersonic, or moving upwards, I guess. Well, this is ascending. I keep thinking it's descending. This is ascending. Obviously, it goes from subsonic, transonic, supersonic, and then to rarefied flow. We use different types of solvers. Fun3D is very popular here at NASA Langley. LoRa, we sometimes use LoRa for hypersonics. But just for MAV so far, we've only been using Fun3D for all supersonic, hypersonic, and transonic, subsonic. Trisonic wind tunnel data has been used only to requantify the uncertainties, so none of that is already in the air database so far. So only the computational fluid dynamics data is in the database, and this really is the basis of our database development. Always predominant CFD, unless there's a gap to fill with other from other wind tunnel experiments. I can take questions throughout the process. Okay, so air database architecture. Like I said, there's many different ways of developing these models. Specifically within our branch, we compile a Fortran code or Fortran subroutines. There's a main subroutine, and it calls different types of subroutines that, these subroutines can either contain data from different flow regimes, or they can also contain function-based routines, such as interpolation or bridging or blending between different flow regimes, curve fittings, and so on. So far, the MAV holds a bunch of subroutines. There's a composite arrow, so we're switching 3 DOF data, CA, CN, CM, into a 6 DOF forces and moments. Then we also have a bunch of other ones where we contain the data. So MAV transition contains the rarefied flow. MAV continuum contains the continuum flow, supersonics and subsonics. Free molecular, free MAV contains the free molecular data. Then dynamics, we have a subroutine for dynamic arrow. We also have some other function-based subroutines like the bridge MAV and the biparabolic interpolations in there. And then we also have dispersions. These are where we carry our uncertainties, adders and multipliers. By definition, we input alpha, beta, Newton number, Mach number based on these flow regimes. Mach number is a non-dimensional parameter, velocity over speed of sound. And as for Newton number, it is defined by the free molecular weight divided by the characteristic length. Again, it describes the sparsity of the air molecules with respect to a characteristic length. And there are cutoff Newton numbers. So if their Newton number exceeds 1,000, we're entering the free molecular MAV subroutine. If it's between 0.0046 and 1,000, it triggers the transition subroutine. And if it's anything below that, then it triggers the continuum subroutine, and Mach number generally becomes an input for the air database rather than the Newton number. Okay, these are just products of our air database so far. All the data that is contained in our air database, we just generally plot them at different conditions. On the left side, you can see this is the pitching moment at the center of gravity with respect to Mach number. Obviously, we've collected all these data from the different solvers, and we populated in the aerodynamic database and with our biparabolic interpolations and other linear interpolations that we call up in these sweeps. This is how the database really generally looks like at different angles of attack. And then on the right side, this is the pitching moment with at center of gravity for various angles of attack at 3 main conditions, 3 main flight trajectory conditions: maximum Q, main engine cutoff 1, main engine cutoff 2. Like I said, main engine cutoff 1 is when we trigger the main engine cutoff. And then there's a transit response until main engine cutoff 2. There's slight differences, but still we need to make sure that the vehicle is stable and trimmed at these conditions. Okay, for the majority of the talk, I will be focusing only on continuum flow and how we obtain data for that, and of course, how we use that data to quantify the uncertainties moving forward. Okay, and there's different ways of populating the aerodynamic database. As someone who's always asking for data from computationalists and experimentalists, you can always populate an aerodynamic database based on, bounding points. This is where the vehicle is expected to reach its maximum operating envelopes. And data can be sparse at these bounding points, and we can just interpolate between those bounding points, or figure out where the vehicle is going to be flying the most at different alphas or betas and Mach number conditions. And then we start populating these conditions, or this window of trajectories with more refined data points than normal. So different ways of asking for information. And obviously, MAV is predominantly CFD data. So for Continuum, again, this is Fun3D. And for this specific supersonic static aerodynamics, fully unstructured Navier-Stokes equation has been performed. Just going to run through what they are. I know some of you are familiar with the governing equations and how Fun3D solves the Navier-Stokes equation. It's a finite volume, node-centered discretization, Spalart-Elmars turbulence model. Uses a second order accuracy, and it generates gradient-based values using the least square Green-Gauss techniques. It does that by integrating fluxes using the trapezoidal rule, where nodal values are extrapolated to the center of the edges. Most of the solution, the gridding, has been performed through the sketch to solution process. So there's many various different types of gridding techniques. Bill Klebb is really leading the sketch to solution process at the aerothermal branch, generating some of these solutions. It's a mesh adaptation technique. And so far, Bill only ran all surfaces except for the vehicle base plane. So it's only four-body data that has been solved here rather than the full wake flow. As for the 14-inch trisonic wind tunnel test data, it's over at the Marshall Space Flight Center. It's a 14 by 14 inch flow down tunnel from pressure storage to vacuum and atmosphere outlets. It's got an interchangeable test section. So it has a test section that can run subsonic conditions from Mach 0.2 to 2.5, and then it can also run supersonic conditions from 2.55 to 5. It's got a controllable diffuser for speed variability. So that means that you can attain certain speed flow at certain Mach numbers. So you can't get Mach 5. You can get Mach 4.96. That's how it's designed, and it's got a remote compressor station for air supply. The test article is 0.0577 scaled. I don't have the percentage in my head right now. What is the scaling from this model to the full scale model? It's an inconel alloy 718, and we had fitted pressure sensors or pressure taps at the base of that vehicle. So we've done some basic pressure corrections to estimate the four-body surface forces only, and that gives us the apples-to-apples comparison between the wind tunnel and the CFD data. Image, so this is sketch to solution, Mach 3.72, that's at 4 degrees, and for the wind tunnel, this is Schlieren, this is at Mach 4.96, 8 degrees. Yeah, of course.
I see your wind tunnel data has sting, and your sketch to solution doesn't look like it has sting. Maybe it does. Does that not matter?
Yeah, it matters in some sense. Obviously, sting is going to affect the wake flow to some extent. And like I said, we've only done four-body forces comparisons only. So we're not taking into account the effects of the wake and how the sting affects or interferes with the wake flow. But obviously, this is a big problem. There's always ways to mitigate that. If you're doing full 3D solutions, the magnetic suspension balance system too has some ideas, or people have been doing some sting corrections in CFD. Yeah, there's various other ways to really refine and mitigate all the uncertainties from there. Okay, so I'm just going to go over the test matrix. There's more wind tunnel data than there is for CFD, but generally speaking, for comparison, we've got 5 Mach conditions: 0.8, 1.05, 1.96, 2.99, and 4.96. Varies from subsonic, transonic, to low supersonic and obviously high supersonic. The alpha sweeps for the CFD ran between -8 to 20 degrees. For the wind tunnel, it's -1.6 to 18 degrees. And when we're comparing, we're doing some linear fits to make sure that we're comparing, apples to apples again. And we've examined different clock angles or roll angles, phi in this case. So we've been rotating. This is not an axisymmetric vehicle. So we are rotating the vehicle at different phi angles, 45, 90, 180, and so on, just to investigate the effect of clock angles or roll angles on the flow. 4 different types of configurations have been tested. The baseline is just a slender body, no ramp. So you can see we can add ramps and we can add protuberances. Baseline is no ramp, no protuberance. Configuration 2, it only has a ramp, no protuberance. Configuration 3, protuberances has been added on the first stage and the second stage, and no ramp in this case. And configuration 4 has everything. And really, configuration 4 is the most representative model for MAV. But again, we're investigating the effects of configurations and how we can bound the uncertainties should we ever change configuration. We can bound these uncertainties using the data that we have. Not given exact dimensions just because proprietary information, but just imagine there are protuberances on these vehicles, and yeah. Okay, static error data analysis. So I'm going to start off with the effect of configuration or geometry variations on both lift and drag. One sample case is shown here. This is the Mach 2.99, which is kind of supersonic, mid-supersonic. And really, there isn't, for the lift coefficient, there isn't much variation. And it's all this primarily entail a small shift in the curve by constant value. And you can see there's a slight increase with the protuberance, and the ramp generates more lift than the baseline case. Really is a linear shift for the lift coefficient. For the drag, you also maintain the same pattern, maintain the same behavior. More variations than we do see in the lift coefficient. So what do we come out of this? Protuberance effects are greater than ramp effects. This is what we've discovered in this case study, especially on the drag, and it's consistent supersonically throughout other Mach conditions. Moving forward, wind tunnel data and the effects of roll angle on rolling moments. So now we are selecting a one configuration in this case, just configuration 4, and you see that highlighted on the top right. We move forward with configuration 4, which is our really most representative case. Vehicle design at Mach 0.8, which is close to transonic flow. You can see some variations in the rolling moment at various clock angles. Again, this is not a fully axisymmetric vehicle, so there's going to be some variations there. And at Mach 1.96, we start getting way more variations in the rolling moment, particularly for the 270 degrees clock angle. Again, these are just, it depends on how the protuberances are actually laid on the vehicle themselves. So observation-wise, rolling moment increases between transonic to supersonic. It increases rapidly for 8 degrees for specific orientations. And really that gives us an indication what favorable roll orientations the vehicle should be really flying through, and how do we establish uncertainties, and how important that we are to establish uncertainties, especially with rolling moments at these conditions. So again, more data, sorry. Yeah. Well, so rolling moment is important. It's a slender body. I mean, blunt bodies, it's a different breed, but slender bodies, they're much more sensitive to flow behavior, especially with ascending vehicles. Ascending vehicles, they propagate instabilities. Descending vehicles, they just wait for instabilities. So it is important to make sure we are analyzing the correct the correct coefficients and how we can bound these uncertainties. So pitching moment in this case, we first things first, wind tunnel data for all four configurations is compared here. As you can see, there's two trim points at Mach 4.96. This is Mach 4.96. I should label that here. And there's a big variation between all four configurations when it comes to the pitch moment. But as we compare with CFD, the red dots is Fun 3D data. The blue dots is wind tunnel data. And you can see you don't really see those trim conditions at lower Mach number, at the subsonic and transonic and lower supersonic. So you start getting these trim points at Mach 5, which is really close to the main engine cutoff. That's exactly where we want the vehicle to be stable. But the big observation is that we get this really large shift in trim conditions at the higher angles of attack based on different configuration changes. And so I've already explained that. Two main observations, that there are two trim points, and you can see there's significant effects of varying geometry on the trim angle of attack. So adding ramps or playing around with the vehicle ramp does play a big role in trimming conditions. And with that kind of data, it can support future designs, whether or not we want to add a ramp or want to investigate or invest in, doing case studies on how ramp affects the trim conditions at higher angle of attack.
Is the vehicle RCS stable, or is just spin stabilized and then let go? Like, as in, do you have 3-axis control or not?
It's spin stabilized for the second stage motor burn. For the first, before separation, I'd have to look at the GNC and see how the RCS are firing. But we do have roll RCS firing in the first 75 seconds of nominal burn. And then we do see some RCS firing, especially for the yaw and the pitch after MECO, after main engine cutoff. So. So yeah, the RCS plane. So yes, the vehicle does have an RCS. So haven't been talking about in this talk, and probably won't be talking. But yeah, the RCS is a little closer to the CG, a little after the CG point. It's a bit tricky. You have to design these RCS so that they are within the gimbal control authority of the vehicle. When you're generating RCS, there's going to be a lagged response of the vehicle. So making sure that the vehicle is close to trim conditions or somehow within the bounds of the trim conditions would help the RCS control and maintain these kind of authorities. But yeah, tends to get difficult if as it moves farther away from the trim conditions at these speeds. Okay, so I promise you this is the last set of data comparison. Actual force coefficient and normal force coefficient for all test cases. Again, this is only focusing on configuration 4. This is where we populated most of the data. As you can see, we generally get some good agreement at higher Mach numbers. At lower Mach numbers, again, this is four-body pressure, four-body forces comparisons. So any wake effects is not going to be included in these data. You can see the largest discrepancies actually happen at the lower Mach ends, the transonic and the lower supersonic, which makes sense. At higher Mach conditions, it's pressure dominated, and the wake flow does not contribute as much as the four-body itself. And same thing with the normal force coefficient. We've got some good comparison here. So I'm just showing you that we've got good techniques at Langley, and that's all I got to say here. Okay, so observation high supersonic data tends to match closer to CFD due to the dominance of four-body pressure in the flow field. Okay, into my last section, the uncertainty modeling. And the way we do things, obviously there are different ways of modeling uncertainties. I know for Orion, they've done individual contribution of uncertainties coming from wind tunnel experiments, from CFD, from other non-correlating factors, developed the root sum squared method to generate uncertainties for Orion, really led by Karen Bibb, which I admire her work in uncertainty modeling. But in our branch, we also came up with, Mark Schoenberg and Ashley Corzon, they've derived these uncertainty coefficients, or how we generate uncertainties for these coefficients based on two main variables, the uncertainty in the adders and uncertainty in the multipliers. Okay, so as you can see, got all these six forces and moments for the forces, CA, CN, and CY. You can see that it has, especially for CN and CY, it has an adder term that is added onto the nominal coefficients, and then there's a multiplier term that changes the slope of your CN and CY plots. As for CA, it only has a multiplier. For the moments, it's a bit different. We have two reference points. We have the moment reference point for this vehicle is the nose, and when we do the dispersion, when we do the apply the uncertainties and adders, they are applied at the center of gravity. So we are dispersing these coefficients with respect to the center of gravity of the vehicle, and you can see we do all these moment transfers, delta x, delta z. If there's a radial offset or there's a axial offset in the CG, we make sure that we do the moment transfers to the center of gravity, disperse the center of gravity coefficients, and then bring it back to the nose for post-2 implementation and other flight simulations. So like I said, adders, these result in trimming the angle, trim angle shifts. It really just translates my nominal plots or my nominal conditions, and the multipliers, we generate these multipliers to change the slope of the curve. And we use these. We use the data that we have to quantify these adders and multipliers. So we can always refine these adders and multipliers, especially closer to trim conditions. And for this study, we are requantifying adders and multipliers so that the uncertainties can cover a range of Mach number, roll angles, and protuberance effects, so geometry effects. As you can see, is also important. We also have some alpha functionalities. Higher angles of attack tend to have different adders and multipliers than lower angles of attacks. Okay, so I'm just going to walk you through the process of quantifying these uncertainties and adders and multipliers. So I'm going to use this classic example. This is pitch moment at Mach 4.96. So we've got all these data plots from wind tunnel tests from CFD at different clock angles or roll angles, 0 to 180 degrees. And you can see it's got these two trim conditions, one at lower angles of attack and one at high angles of attack. So we can generate adders and multipliers based on alpha functionality here. As you can see, we can move forward with taking an ensemble average of all the CFD data and an ensemble average of all the wind tunnel data. They do agree pretty well at these Mach 5, like I said, because of the pressure dominant flow field. And from there, we can split the curve. We can split that into lower angles of attack region, high angles of attack region, and we can provide just a very basic linear fit. And these linear fits, you can almost see they have different slopes, meaning that the flow physics, or however the differences in the flow physics can be accommodated from the adders and the multipliers. So we do generate. We try to transfer the trim conditions so that they match. This is plot C, so we're trying to bring all these plots, the CFD plot and the wind tunnel plot, so that they can match at 0 angles of attack or the trim conditions. So we are transferring that, or we're translationally mapping those at the trim conditions. This is how we obtain our adders, and then we iterate the slopes such that these slopes can match with each other at low angles of attack and high angles of attack. And once we match the slopes, we can obtain the multipliers for this case. It's a tedious process, but it works. For the most part, obviously, if you get good comparisons, it gets really hard. But generally speaking, this is how it's been done for most of the data comparison. And so in the database, we can always accommodate some alpha functionality in terms of uncertainties. So for this case, for this example, from 0 to 8 degrees, we got adders of 0.03 and multiplier of 12%. And if the vehicle flies at over 8 degrees, then we've got a new set of adders and multipliers for these conditions. So let's test these adders and multipliers, and let's bound our all of our data sets. And you can see it bounds them pretty well, with the exception of one data, and that's I believe that's at 90 degrees clock angle. And that's fine. You don't have to always bound every single data set. You always have to strike a good balance between being aggressive and conservative when it comes to uncertainty modeling, especially in how you apply to dispersions and flight trajectory analysis. Okay, so the reason this specific case or outlier is not bounded at higher angles of attack is probably because the protuberance is actually extruding into the flow, and so hopefully the vehicle does not really fly at this angle, but still it's good to make sure we bound all these unknowns and have a good balance between aggressiveness and conservatism. Okay, so this has been done for all test conditions for axial force, side force, normal force, roll moments, pitch moment, and yaw moments. And in the database, these uncertainty adders and multipliers, they also have mock functionality. So if the vehicle is flying 0.8 and lower, it's going to use that set of adders and multipliers. If it's flying between 0.8 and 1.05, there's an overlapping window, and it's defined in the error database to some extent. There's also interpolation between these adders and multipliers. So if you're calling in between 0.08 and 1.05, it interpolates. If you call somewhere close to 105, it uses that set of data, and so on. And anything beyond 4.96, it uses extrapolates these uncertainties and adders and multipliers at these conditions. As you can see, the hypersonic conditions or the high supersonic conditions carry less uncertainties, and that makes sense because of how well the pitch moment and other coefficients agree at high angles, at high Mach numbers. At lower Mach numbers, obviously, the four-body force comparison it needs to be refined more. So we need to maybe run more wake flow analysis and refine the uncertainties at these at lower Mach conditions. You can see we're getting 12% for multipliers to the axial force. We got 25% for CMCG and 0.8 and 105, and obviously it drops as we're increasing Mach number. Obviously, we don't have any wake flow discrepancies here. And here's a test of these uncertainty bounds. The blue line is what is actually derived from the study. The red line is what we normally carry from heritage and past missions. Supersonically, it's plus and minus 10%. That's at Mach 4.96. So we definitely did refine. We don't want, again, conservatism in our uncertainties. We have the data to speak the facts. And same thing with the right plot. This is normal force. Again, we have refined our uncertainty bounds, still bounds these discrepancies pretty nicely. And how these bounds actually look in our error database so far. If you look at the bottom left plot, you got the axial force. It bounds it pretty nicely again. No issues there. At the right plot, you can see the bounds. The nominal is the blue line, and then the black lines is basically your dispersed. Monte Carlos are ran plus and minus 1. These are the maximum bounding windows. And so the only big issue here when we refine our uncertainties is that when you look closely at the trim conditions, we want to make sure that the bounds or the uncertainty bounds actually track well with the nominal. We don't want them to be too separated because in the end of the day, you don't want to have a dispersed trajectory that is not trimmed. So it's very important to always have these refined uncertainties, especially close to the trim conditions, and that's what we've been doing here. In conclusion, for this plot, for this slide, sorry, plus and minus 3 sigma uncertainties shown with the blue dashed lines, and the red dashed lines is based on Mars flight heritage, plus and minus 10% for supersonic conditions, and wind tunnel analysis yield higher fidelity uncertainties. So we've successfully refined our uncertainties using wind tunnel and CFD comparison for this study. Okay, favorite part, conclusion. Demonstrated an overview of MAV's aerodynamic database development based on the mission that has been described, especially for the first stage burn trajectory points. We've observed several effects of vehicle geometry, especially with the ramp and the protuberances. They affect our pitch moment and roll moments, and we've used that data to bound our uncertainties in case we do have these geometry changes when it comes to future designs. But also it also informs us where we can sort of alter our ramp effects or protuberance effects so that we can attain favorable trim conditions and roll stability. We've used static supersonic aerodynamic data comparison between CFD and wind tunnel data sets, and we've used those 2 data sets to refine our adders and multipliers. They were based on Fun3D and 14-inch by 14-inch trisonic wind tunnel data. And then the uncertainties, they've been expanded as a function as roll angle to capture protuberance effects, and they also have some Mach functionality and angle of attack functionality in the aerodynamic database as of now. Future work, obviously we talked about RCS. It's still in the works. We've got 6 RCS jets initially, and then now they're converted to 8 RCS jets. We're doing some CFD on that, and obviously RCS jets require uncertainties, so we also have these subroutines to develop. But also, if you ever question the methodology that we've used here, there are many other different types of methodologies that can be used. Like I said, Karen Bibb has been leading some great work with uncertainty modeling on the Orion, and this is definitely some avenue of potential work for a potential intern to explore this model, maybe. If you guys have interns, sure. If not, then there's always ways. Like I said, this is the model that Karen Bibb have been using is obtain individual contributions from a CFD sensitivity study, obtain individual contributions of wind tunnel uncertainties, and then there's also many other different types of uncorrelated sigmas or uncorrelated uncertainties, like a configuration change or a roll angle or geometry symmetry, or even uncertainties between Earth and Mars conditions. I mean, how do we quantify these kind of sigmas? It's very, very, very important.